Ladies and gentlemen, glad that you are joining my presentation. I'll be talking on numerical modeling and simulation of spiral reinforcement in prefabricated bridge columns. Uh, I would like to acknowledge my colleagues, Mr. Luboš Řehounek, Czech Technology University in Prague, and Radomír Pukl from Červenka Consulting. My name is Jan Červenka. So I'm talking about results which were obtained in a project funded by Czech Technological Agency, spiral reinforcement, which has been developed in Taiwan by company Ruentex in cooperation with NTU and NCREE Taiwan. As you can see, this spiral reinforcement compared to traditional reinforcement, which is typically organized in these kind of square shapes, has the advantage that it provides more confinement, so that as you see in these contour plots, you may obtain higher confinement inside these spirals than in the classical reinforcement. And this provides, of course, higher load carrying capacity, as we can see in these graphs on top. Participation in this project was mainly on modeling of this spiral reinforcement. For that, I would like to say a few words about the material model that we are using. So we are using software Athena, and there we are using the fracture plastic material model, which consists of a orthotropic smear crack model to model cracking and plasticity-based model to crushing of concrete. As you see at the bottom, this is the plasticity criterion we are using in the plastic part of the model. First, this plasticity opens and develops to simulate hardening part in the response, and then when the compressive strength is reached, we reach the softening. So the softening, both in compression and in tension, is governed by approach analogical to the crack bend model. That means we have a crack bend size. In tension, this size is equal to the projection of the finite element size into the direction perpendicular to the cracks. In compression, it is the size of the element in the direction along the maximum compressive stress. So with this approach, we can capture the proper energy dissipation. And in addition, we have to take into account the fact that when the crack propagation, as you see here, for instance, in this kind of rectangular element, but you can understand that analogical approach can be used also for 3D brick elements. So when the crack direction is not perfectly aligned with the finite element edges, as you can see here, so that there is some angle theta, it is clear, like we see in this schematic figure on the right, that when the crack propagates in a diagonal way with respect to the finite element mesh, the cracking will not be localized into a single row of elements, but will be kind of zigzagging through the mesh. And basically the localization will have to involve more than one element. To account for that, we increase the crack bend size by this gamma factor, which depending on the angle of this crack inclination with respect to this ideal direction, increases up to 50%. Well, in addition to this standard normal behavior, we also have to address the situation of strength, shear strength of the cracked concrete, or shear stiffness of the cracked concrete, and shear strength of the cracked concrete. So the shear stiffness of the crack is assumed dependent on the stiffness in the normal direction multiplied by this factor SF, which is then calibrated based on experimental results to be 20. And for the shear strength, we are using the formula from the modified compression field theory, of Collins and bends. Another feature which is useful to take into account in reinforced concrete subjected to cracking is the reduction of compressive strength when we have a cracked concrete. That means when concrete cracks in the direction perpendicular to the cracks, we can still obtain some, can still develop some compressive stresses, but it has been experimentally proven by Collins and Benz that this compressive strength is being reduced by the presence of cracks. And we are using the empirical formula that they developed to take this into account. All right, so I'm coming to the experiments that we'll be simulating. So these are experiments performed in Taiwan at NCREE. This very large testing machine. They call it METS, multi-axial testing system. And the experiment that we'll be analyzing is being subjected to this kind of increasing cyclic loading. And you see visual picture, photo of the specimen after the test. So you see all the damages, cracking, and so on. So nicely see how the concrete is confined by the spiral reinforcement. So this is our model. We are using brick elements, isoparametric linear brick elements. You see we are using quite fine mesh for the middle part, which is column which we want to test. You see inside the column we have this spiral reinforcement. How do we model the reinforcement? We are using the embedded approach, which that means when the program starts, we search for the intersection of the reinforcement with respect to the 3D finite elements. And at each integration, at each intersection, we place truss elements with multilinear stress strain diagram and Meningotto-Pinto cyclic model. It is important, of course, also to consider the bond, possibility to lose a bond between concrete and steel. And for that, we account by adding additional degrees of freedom at each reinforcement node representing slips. And then we can apply a slip law at each of these nodes. We are using the FIV model code slip law. And in addition to simulate cyclic behavior, we are using this kind of hysteretic cyclic model to account for the hysteresis during the cyclic behavior reinforcement. So let me show an animation of such an analysis. So what you see on the top left is the load displacement diagram, and there is a point moving on the diagram showing exactly where the results, where we are in our analysis. The middle plot shows the deformed shape of the structure with the cracks as they open and close. And the contours, they show the equivalent plastic strain, which represents the level of crushing we can estimate from that. So when we are in these blue colors, this means the concrete is fully crushed. That means the compressive strength of concrete was reached. And then this plot on the right, which I think is now a little bit behind, this shows the stress strains in the reinforcement. And when we see reinforcement reaching this red color, this means we have a rupture of the reinforcement. So if I go to the end, to see how this reinforcement, when we are reaching this end of the analysis, how it ruptured. So mainly at the bottom, tensile reinforcement actually, and you see that what ruptured is the spiral reinforcement, those side spirals, and also in the sides, side spirals, and also in this middle spiral. So here we see the comparison of the load displacement diagram from the experiment. So it's quite good. Of course, if we would fine-tune the model, we can obtain a better match, but we want to use really the parameters, basic parameters, just generated based on the concrete compressive strength, which is what engineers usually information they have. And we see here the stresses in the reinforcements at the peak load and the cracks at the peak load, as well as these crashing areas indicated by this blue color. So let me summarize. So I presented a development of a model for this spiral reinforcement RC elements. Spiral reinforcement is a very effective method, especially for prefabricated structures. They allow to have a very automatic way of production. And the model that we developed is using plasticity for concrete in compression, orthotropic smear crack model for cracking using the crack band model, multilinear reinforcement, stress strain law with Menegotto-Pinto cyclic model, and important is also that we take into account the cyclic behavior of reinforcement bond. So the developed model is used for the optimization of this design of the spiral reinforcement for prefabricated columns, mainly for seismic regions. So with this, I would like to thank you very much for your attention, and I'll be happy to answer any of the questions in the Q&A section. So thank you again, and see you later.